In the last module, we presented definition of what is convection. We went through classification of convection in terms of how the flow is happening, whether it is internal or external flow. Many times students have a lot of confusion, I would say, about what is the temperature, what is the velocity that we need to use, and that is why we try to write things in perspective. As in case of internal flow, we are going to have certain quantities. In case of external flow, we are going to have certain quantities. What are they? We wrote, if we have internal flow, we are going to have, let us just write external flow. We have u infinity, we have local u of x comma y, t infinity, t of x comma y. Okay. Internal flow, on the other hand, we have u infinity, u of x comma y, u bulk mean. T infinity, of course T wall is also there, sorry, T wall could be constant or a function of x, T infinity, T of x comma y, T wall which could be a constant or a function of x, and more importantly T bulk mean, which is going to be the bulk mean temperature or the mixing cup temperature. This and this are specific to internal flows. I have written here x comma y, this would be r comma z for pipe flow. It is just a convention, does not matter. The idea being, you have to have what is called as a bulk mean temperature and the bulk mean velocity. What are these quantities? In your fluid mechanics, you would have started off the definition of bulk mean velocity by equating the mass flow rates. So, if this is the velocity profile u of r comma z, and this is the average or the bulk mean velocity which is given by u of m bar, you would say m dot, which is evaluated either as a rho u dA over the cross sectional area, is nothing but rho actual cross sectional area times bulk mean velocity. For an incompressible flow, rho will cancel off and you have u m is 1 over AC integral u of r comma z dA. This is 1 over pi r square. If this is my r, this is my z, and this is r equal to capital R, integral 0 to r u of r comma z 2 pi r dr. How do you get 2 pi r dr? Area is pi r square of a ring. You have the pipe. This is a ring at radius r of thickness delta r. So, dA is nothing but 2 pi r dr. So, this is what we substitute here, and u bulk mean therefore is nothing but 2 by r square, the pi's will cancel off, 0 to r u of r comma z dr. This is your average or bulk mean velocity, whatever be the velocity profile. If it is a laminar velocity profile, it would be a parabolic profile. If it is turbulent, it could be some other kind of profile. Whatever be it, the average or bulk mean velocity is defined like this: average or bulk mean velocity. This quantity is used to calculate gross quantities like flow rate. Volumetric flow rate is A into bulk mean velocity. Okay, mass flow rate is rho A u m. When I want to calculate quantities for friction factor is, if you remember, laminar flow 64 by Re for a pipe flow. This Re definition would be rho u bulk mean d by mu. So, in these definitions you have this average velocity. What is this bulk mean temperature then? Bulk mean temperature or mixing cup temperature is nothing but, it is a very simple concept. You have a temperature profile which is like this. T wall, which is a function of x, T local, which is a function of r comma z, I will call this z, sorry. Z is the flow direction. I consciously use Z as opposed to X because X can refer to quality in two-phase flow, and since I am a two-phase flow person, I like to use Z here. And this black dashed line is the so-called bulk mean temperature. Remember, in heat transfer, there's a very big change compared to hydrodynamics. In hydrodynamics or fluid mechanics, this velocity profile is going to be the same at any z location. U of r comma z is not a function of z. That is what is called as fully developed flow. Fully developed flow. Remember this? Therefore, if I take a snapshot of the velocity profile at Z1, the snapshot of the velocity profile at Z2 or Z3 or any Z is identical. I have not drawn it identical, but that is my limitation. What I am trying to say is the equation, the values, everything would be identical. The profiles of velocity at any two arbitrary z location beyond hydrodynamic entrance length, that is when your flow is fully developed, the profiles are identical. So du by dz is 0. This is extremely useful in simplifying our governing equations. Now, in heat transfer, what is heat transfer? You are dumping heat into the fluid is transporting energy. So it should when I take in heat, what is the manifestation of heat? Temperature. You and I know temperature. So at this location, say Z1, temperature is T bulk mean 1, T wall 1, correct? TW1. I have not yet defined bulk mean temperature. I will do so in a minute. Water at 25 degree enters the pipe, leaves at 40 degrees. What does it mean? If I took the water, put it in a cup, insulated, mixed it very well and put in a thermometer, the temperature the thermometer would measure is 25 degrees. This is called as a mixing cup temperature or bulk mean temperature. This is a number you and I will know. Okay. Now, if the fluid is passing through a pipe through whose walls heat is being supplied, that means it's going to get heated. So water comes in at 25 degrees, goes out at 40 degrees, that means it has gotten heated by 15 degrees. Who is supplying the heat? It is coming from the outside, either electrical heating or whatever. So the fluid temperature is changing with respect to Z at every location. Is that a valid statement? If the fluid temperature is changing, obviously the wall temperature also, the location through which the heat is being transported, is also becoming slightly hotter than before. So I am going to have a T wall which is now slightly bigger than here. So I will draw, because of my limitation, I am going to draw this slightly different. So you can notice this one, the lines here which are manifestation or representation of the temperature are smaller than the lines here which are a representation of the fluid temperature. T wall 2 at Z2 or T wall at Z2 is going to be greater. Energy content of the fluid has increased. This was 25, this is now 30, for example. Energy content has increased, that means the bulk mean temperature has increased. Internal energy, which is a function of temperature, is what you see. You don't have an energy meter, but you say water at 25 degree, it has a particular energy content. Water at 30 degree has a slightly higher energy content, and you know from energy balance, Q double prime pi d, or let me write this step by step, E dot in minus E dot out plus E dot generated equal to E dot stored. This all of us know. What is E dot in? If I take this control volume of a fluid, E dot in is m dot Cp, bulk mean temperature is T bulk mean, m dot Cp T bulk mean plus dTm. We have not defined, just take it as T for whatever it is. So temperature has gone from T to T plus dt. Okay, I'm using this subscript Tm, can use that also. And if the heat flux is Q double prime, this could be constant or varying, doesn't matter. So we can write steady state, no heat generation, constant properties. All these assumptions would give me E dot in minus E dot out plus E dot generated equal to E dot stored. This is steady state, so this is because of 1, because of 2 this goes to 0. E dot in is m dot cptm plus q double prime pi d dz. The diameter of the pipe is capital D, and heat flux times the surface area DAS, that is equal to m dot Cp Tm plus dTm. Heat is being added, so the temperature is increasing. Because the temperature is increasing, this has become Tm plus dTm. So if I simplify, I get q double prime pi d dz is equal to m dot Cp dTm. In other words, dTm by dz is equal to q double prime pi d by m dot Cp. This is a favorite equation, very useful, gives you a lot of things. What is this? Q double prime, constant. Pi is a constant, m dot is a constant, d is a constant, Cp is a constant. That means what? dTm by dz is equal to constant. What does this mean? Temperature gradient with respect to the flow direction. That means T at Z2 minus T at Z1 divided by Z2 minus Z1 is constant, and it is greater than 0, right? Everything is positive here, so this is greater than 0. That means T bulk mean at Z2 is greater than T bulk mean at Z1. Obviously, I didn't have to go through this to tell you that, but important thing being, this definition of dTm by dz we will use later again in the later modules, is telling you that it is a straight line. Variation for constant heat flux case, T bulk mean versus Z is a straight line variation. Very important, very useful concept. Okay, so bulk mean temperature is increasing, energy content is increasing. So what is the difference? Here the velocity profile was identical, du by dz is 0. The temperature profile is not identical. Please remember, T of r comma z not identical at all after merger of boundary layers. Please remember, T of r comma z is not identical. You have profile at a further downstream location, it would be a greater wall temperature than before, than here, something like this, okay, or something even thicker like this. The point being, I am not going to have one profile, or if I take a snapshot, the same thing would be repeated at different z locations. No, in heat transfer, because I am dumping heat physically into the fluid, the temperature locally is changing, the bulk mean temperature also is changing. So the problem with heat transfer as opposed to hydrodynamics is that you have one major additional complexity which is there, and that complexity is the fact that your temperatures are changing locally. So I have T wall Z2, T bulk mean Z2, T wall Z1, T bulk mean Z1, T local Z comma R, T local z1 z2 comma r, t local z1 comma r. At the same z location, these are all going to be greater when heat is added to the fluid. T infinity of course was constant because T infinity was a free stream. What was entering? We didn't bother about it. Okay. So, if I now want to define this so called bulk mean temperature, it comes from energy balance. E dot in minus E dot out equal to 0, or if I write energy content E is m dot Cp T bulk mean. This is the energy content. Flow rate, therefore it is E dot. What is m dot? Rho cross sectional area U bulk mean Cp T bulk mean, which I have to define. Correct? So, this quantity is nothing but E, energy calculated by integration over the cross sectional area. What is this integration? This is nothing but m dot dm dot Cp T of r comma z. So, I have this ring of fluid whose area is dA. This is my ring of area dA, whose temperature is T of r comma z, whose velocity is u of r comma z. This is a part of a larger pipe whose radius is capital R. Okay. And this quantity, this shaded area, has a particular energy content which is given by delta m Cp into T of r comma z. When I integrate this over the entire cross sectional area of the pipe, I would get the same energy content as given by this formula, and here this is the unknown quantity. So, dm is nothing but rho u of r comma z dA C Cp T of r comma z, and this is equal to E dot. So, let me equate from the previous slide. Rho AC um bar Cp T of bulk mean, which I want to find, is equal to integral rho Cp u of r comma z T of r comma z 2 pi r dr 0 to capital R. This is the limit, r equal to capital R equal to 0. Rho cancels, Cp cancels, Cp cancels, constant properties, nothing is changing. This would be pi capital R squared. I have defined average velocity before in the earlier set of slides. This is my average velocity, slide number 5 earlier in the module. So, this would be a number, or I can also substitute for this directly. So, I am going to write T bulk mean is equal to integral 0 to capital R, 2 pi comes out R u of r comma z T of r comma z dr divided by AC pi capital R squared. If I want, I will put it as 2 by capital R squared into R u of r comma z dr 0 to r. 2 pi, everything cancels. I am left with R u r comma z T r comma z 0 to r dr divided by this one. Okay, or I will just choose to leave it as T bulk mean is equal to 1 by bar 2 pi cancels. So, this will be 2 pi by r squared. So, if I do not substitute for I am going to have as it is. AC would be pi capital R squared. So, I would be left with 2 by r square into this. So, the same expression, if I substitute for I would get this. If I leave as it is, I would get this. The point being, bulk mean temperature is a function of r and z, the function of the local velocity distribution and the temperature distribution, the average velocity. Is this a constant with respect to z? No, because my fluid is getting heated or cooled. So, this is going to be a function of z. I have a velocity profile u of r comma z. I have a temperature profile which is given by this. The product of this is u into t. So, every r z location, I take the velocity, I take the temperature, multiply that into r integrated. So, it is this combined curves which are going to move in the z direction. This velocity curve is fixed, the temperature curve is going on becoming bulkier, it's going bulging in the center and at the wall because heat is being added. So, at next location I would have the temperature curve, I do not have a different pen, I would have a temperature curve which looks like this. So, I am going to have a bigger number for t. So, this is t of r comma z, this is earlier t of r comma z1, z2. So, the temperature profile curves are going to become bigger and bigger as I move in the flow direction. So, bulk mean temperature or mixing cup temperature is also going to become higher and higher along the flow direction. So, this is the definition of the bulk mean temperature. So, having defined this bulk mean temperature, we now have understood that in addition to free stream velocity, in addition to free stream temperature, we have additional quantities specific to internal flow, which are these. And therefore, for me, I have 1, 2, 3 variables that define the velocity in internal flow. Here I have only 2. Here I had 3 for temperature in external flow. I have 4 quantities that I have to take care of: local, average, infinity, wall. Infinity here will not be that important in internal flow. How the fluid came in, what velocity it came in, what is the temperature it came in, these two may not be so important. So, we will be handling u and we will be handling t, tw and tm. So, the role of T infinity is in external flow is taken over by T bulk mean. So, this T infinity is kind of insignificant, this u infinity becomes kind of insignificant. So, what was u infinity here is now u bulk mean here. Definitions are of course vastly different. What is T infinity here is going to be here. That is what when I wrote in my first slide, of this lecture, I said the T wall minus Tf, Tf was T infinity in external flow, Tf will become T bulk mean, and we have defined that now. Okay. So, moving on, so we will have, this is slide number 8. We have to define our quantities now. So, heat transfer coefficient we have seen is nothing but Q double prime divided by delta T is equal to heat transfer coefficient. What is this heat transfer coefficient? So, when a flow happens over a solid surface, this is the solid surface, this is T wall, we have this so called thermal boundary layer which is developed, the temperature profile looks something like this. This is T of local x comma y, and let me say this is y, this is x. The first layer of fluid in contact with the heated surface is at T wall, correct. So, the layer of the fluid in contact with the heated surface has 0 velocity. So, the mechanism of heat transfer is primarily conduction. So, H into delta T, some delta T is equal to minus K dt by dy at y equal to 0. This is conduction heat transfer through the first layer of fluid. This first layer of fluid is just transporting energy from the wall to the second layer by conduction, and this is being carried away by the fluid, and therefore it is H delta T. So, minus k dt by dy is equal to H delta T. Therefore, H is equal to minus k dt by dy at y equal to 0 divided by delta T, which is nothing but T wall minus T fluid, and we saw earlier this T fluid could be whatever, T infinity or T bulk mean, depending on what we want. So, if it is internal flow, it will be T bulk mean. If it is external flow, it is T infinity. So, this is the definition of heat transfer coefficient. Heat transfer coefficient, as we said, can be of two types. This is a local, this can be average. What do you mean by this? Local heat transfer coefficient means H is a function of the flow direction. Heat transfer coefficient at every location. So, Q double prime is equal to H delta T. If I am talking of a constant wall heat flux case and I am going on heating the wall, T wall is going on increasing, T infinity is constant, the heat transfer coefficient. This is constant, this is T wall minus T infinity, this is constant, this is going on increasing, therefore, the heat transfer coefficient is going to reduce to keep the product same. So, H is going to drop like this in flow over a flat plate. This value at every location is local. Local means at every location. If I want to take an average value H bar is nothing but integral over 0 to L H local as a function of Z. This is called as the average heat transfer coefficient. Both local and average heat transfer coefficient are useful, very powerful tools wherever we want to take electronic cooling. We have multiple chips on a surface. What is the cooling of this chip versus this chip when you have some velocity going like this? Here I would talk about a local heat transfer coefficient. When I want over the entire surface, I would talk about the average heat transfer coefficient. Last but not the least, we have to define a non-dimensional number, Nusselt number, which is defined as Nu is equal to H into characteristic length by the fluid thermal conductivity, H into X by Kf. Internal flow, I am just writing in black subscript, the X is replaced by D, just as your Reynolds number definition, Rex rho u infinity X by mu, Red rho u bulk mean D by mu. Whatever is the characteristic dimension for Reynolds number, the same is the characteristic dimension for Nusselt number. The heat transfer coefficient here is average, you would have an average Nusselt number. If you talk of local, you would talk of local Nusselt number. This is thermal conductivity of the fluid. This is thermal conductivity of the fluid. Unlike Biot number, which was Hx or H characteristic dimension by thermal conductivity of the solid, that represented the relative importance of the conduction within the solid and the convection on the outer surface of the solid in transient conduction. This refers to a non-dimensional value for the heat transfer coefficient. This is called as the Nusselt number. In the next module, we will just talk about the importance of Prandtl number in heat transfer, convective heat transfer, and then go to classification based on 1D, 2D, laminar flows, all these which we have seen in fluid dynamics, and then talk about what we call as the Reynolds transport theorem. So, acceleration of a fluid particle and Reynolds transport theorem. Thank you.